You can start whenever you're ready.
All right.
Yeah.
Hello, everyone. I will kick us off. I'm Samuel Byler. I'm a rising sixth-year grad student at the University of Toledo, and today I'm going to tell you a tale of two molecules about how atmospheric models overestimate phosphine and underestimate CO2. So here are four objects ranging from T8 to Y0, so about 600 Kelvin objects, looking at So we have three different models here, ATMO 2020, Alpha Low Z. And if you look at them all, most of them have this strong phosphine feature here that we're just not seeing in the data that's in black. And if you look at the data, you see we have the CO2 feature that just isn't in our models. And so we took the ELF-AL atmospheric models and added two parameters to parameterize CO2 and phosphine. So we increased CO2 abundances, and decreased phosphine abundances, and we get much better fits to our data. We find out we need about half the phosphine that is currently in the atmospheric models and at least around 1,000 times increase of CO2. And so if you have any questions about what chemical processes are causing this, come find me in my poster. It's a little too long for this talk, but this paper was just accepted 2 hours ago, and so will be on arXiv on Wednesday. So
Hey, everybody. I'm Kyle. I'm entering my final year of grad school at the University of Texas. And I wanted to advertise the results of a JWST Cycle 2 Director's Discretionary Time program that I'm leading with William Balmer, who's, I think, somewhere here. And the goal of this program is to image the giant planet AF-B at thermal wavelengths with JWST. AF-B is at a really challenging separation to recover with JWST. It's at only about 300 milliarcseconds, which at 4.4 microns places the planet 2 lambda over d away from its host star. And so that already makes it really challenging. But another challenge that we have to contend with is that the coronagraph at that separation blocks most of the light of the planet. You can see that here on imaging taken of the planet HIP 65426b from the ERS program. And even at this wider separation of 820 milliarcseconds, about 10% of the light of the planet is blocked out by the coronagraph. But of course, as you work your way inwards, here's where 25% of light is blocked. Then here's the separation where 50% of the light is blocked. And then 75%, or wait, 75% of the light is blocked. And then here's where 90% of the light is blocked out by the coronagraph. And then here's where AF-B falls. So it's a really challenging planet to recover. We're really pushing the instrumentation to its limits here. But of course, we figured we could do it. We convinced ourselves we could do it. Here's what our prediction was, but you never know until you get on the sky. So what did we observe? Here's a prediction, and then here's what we observed. So if you want to hear more about this data set and what we're learning about the planet, come find me at my poster. Thank you.
Yes. Okay. Hello, my name is Rodrigo Ferrer Chavez. I'm currently a first-year grad student at Northwestern, working with Jason Wang. And as we speak, I got an email that FedEx is done printing my poster. So I'm gonna, after I give the talk, I'm gonna run to FedEx to get my poster, and you'll be able to see it. In the meantime, I have a little cartoon drawn in there. But what we're doing here is basically working in improving numerical subtraction techniques for JWST. So as we have seen, like, it's important to subtract starlight to reveal fainter planets, and that allows us to discover fainter planets. So for example, sub-Jupiter mass planets with JWST. So currently, as we have seen, as we will see more during the week, most of the current algorithms are based on principal component analysis. So like, for example, taking images of reference stars, taking principal components and subtracting those from your starlight target image so that you can hopefully see the planet. We're exploring the limitations of a forward modeling approach, in which we use a differentiable coronagraph model that we wrote in PyTorch, and we try to fit for the optical aberrations, for example, in the optical path differences in the optical telescope element of JWST. And by iterative gradient descent, we fit for the optical aberrations so that we can refine our estimate of the PSF. And here are just some preliminary results that we found from applying our work to simulations. On the left, you see like the initial image. On the middle, you see what you would get if you try to simulate that image with the FITS file configurations of the instrument. So say like at a given date, the optical path difference at a given date, for example. And what you see on the rightmost panels is what you see after performing the iterative gradient descent optimization process, which we can see some planet signal that we injected there. So yeah, that's work. Thank you.
Okay. Hello everyone. My name is Ziying Gu from the University of Tokyo. I'm a PhD student and a member of SKEXAO Spalloo Telescope team. And my topic is about building an empirical model for planet formation, evolution. Sorry. And from the first talk of today, one question is about how we estimate mass from direct imaging. Yes, we mass from theoretical model. We estimate mass from theoretical models. Here are some like model imaging the hot start or cold start initial conditions, but it's kind of hard to get some precise mass measurement. So our new survey want to solve these questions by measuring the dynamical mass measurement and with a higher yield, targeting on accelerating stars. Such acceleration, we believe, comes from potential massive companions around the host stars. And also, we may measure the initial condition, initial entropy to determine the initial conditions. Yeah. And here is the current work on brown dwarf. Yes, we also consider the brown dwarf because they share some similarities in the evolution and compositions. And here is the primary result from my work, and it's generally consistent with the previous results. And here is a new observation from Spalloo Telescope, and a new BD candidate it was detected recently, and we will start analysis soon. So if you're interested in it, feel free to chat with me. Thank you.
Hi, I'm Nico from City University of New York. I'm thinking about systems like this picture where we have a white dwarf star of the size of about the Earth. These are so small targets to be transited, but they could be transited by a very close-in planets. But most white dwarf stars are probably have distant planets that they never transit. One way to detect is distant planets is from the transit timing variations of an inner planet, as the white dwarf and the inner planet are orbiting through the center of mass of the system due to the reflex motion. As we can see here, for an outer planet of 1 Jupiter mass at 10 AU, we can see the transit timing variations of about 16 seconds peak to peak. I calculated for a wide range of masses and distances. And as we can see here, for distant planets, for massive planets at the large distances, we can see that we can have TTVs for about many minutes that they probably could be detectable. So we think this is the promising way that we could discover distant planets around white dwarfs. And these planets also could be a good target for direct imaging. Feel free to stop by my poster.
Hello, my name is Richard Lin. I'm from University of Aurora and right now second year graduate student. And my topic is about studying the dust around how the dust will impact the direct image. So next generation, we are planning to design the instrument that are able to direct image Earth-side exoplanets, but we will meet the problem that how the dust will impact our direct image. And this is my model. So I built a dust model and think through different poses and compare in different methods what the dust background noise will change, and we can finally study in different cases that different telescope size and different inclination of disk. And we can finally get a result that the dust should play the role the image, and we should consider to minimize the impact of dust. And that's all.
Hello everyone, I'm Peng Yu. I'm a final year PhD student from the University of Edinburgh and Leiden University. My poster is about a new planet candidate we discovered from the Young Science Exoplanet Survey. If you want to know the detail about this survey, welcome to see Richel's poster. We named this new system as YSIS-3, as this is the third planetary system we discovered from the YSIS survey. The central star we resolved to be composed of two stars, with the brighter star as a young solar mass star and the secondary star as a M dwarf. And the planet candidate is this very thin source between these two bright background stars. And this candidate is located at 5.3 arcsecond away from the central star, which is more than 705 AU array. And we monitored this planet in 5 years, and we found that this planet only co-moves with the primary star of the binary. And how this could be possible, because this planet is at a very wide situation of the central stars, and it is a binary. So we also found out that the fainter star only shows linear motion to the primary star in 6 years. So this makes us question if the central stars are bound to each other or they are just a chance alignment. So we did the orbital fitting of this system and found out that the secondary star has to be as heavy as the primary star. And I also did ACD fitting and a video velocity measurement of the two stars. All the results are unrealistic for the scenario that the two stars are bound to each other. So we think the central stars are unrelated two stars. So if you want to learn more about this story, welcome to see my poster.
This project was done in collaboration with Juliet Becker, and I'm Thomas McLean, rising senior undergrad at Caltech. And for my project, first of all, the sort of overview interesting element here is that in systems with hot Jupiters, for the most part with nearby companions, for the most part, we see sort of a similar structure, but there's this very unique system, WASP-47, which has an nearby outer companion. So sort of if we look at one of the other systems like TOI 2000, and we imagine that it has an outer companion that perhaps we haven't detected, and then we simulate through stellar evolution, we see, according to varying stellar obliquity, that a lot of the time there's a low probability of that planet transiting, so we wouldn't actually detect it. And looking at a sort of like WASP-47 model system, if we move around the actual nearby outer companion in the sort of darker regions right here, these areas, we would not be able to actually detect that outer companion that we have detected using transit. And if you want to learn more, poster 33. Yeah, thank you.
Hi everyone, just gonna start that. Okay, my name is Mathilde. I'm a postdoc at Space Telescope and Johns Hopkins University. And my poster is presenting a work that is part of the European GTO team ExoMIRI, so of exoplanet observed at mid-infrared wavelengths with GWST. So they are among the first exoplanet observed at these wavelengths, thanks to the MIRI chronograph that are operating at 10, 11, 15 for the 4-quadrant phase mask, and at 23 micron for the classical LEO mask. And the mid-infrared wavelength range is offering many new advantages, so favorable contrast, interesting for exoplanet atmospheric characterization. We can get new photometric points at longer wavelengths, so we can get more precise measurements of temperature and radius. And these are the results that I'm presenting in my poster. So we have 3 systems. The first one is HR8799, which is a study already published led by Anthony Boccaletti, my former PhD advisor. This is revealing the 4 planet, but also an inner emission contribution to the inner disk. We also have the result of SG95086, which is a paper that we submitted a couple of weeks ago, actually. So revealing again the inner disk and also the planet and very bright background object. And the last result that is still ongoing work is the system JG504, which is a system for which we apply a different method to be able to reveal the planet, as we didn't have any reference star observation. So if you want to know more about what we can learn with these mid-infrared images and how we manage to get all of these images, just come to talk to me at my poster. Thank you.
Hi, my name is Cameron. I'm a second-year master's student at the University of Victoria. And the data I'm presenting today is from this collaboration with all these wonderful people where we did NIRCam's Cycle 1 GTO program to observe these 5 famous protoplanetary disks in the hope of detecting new planets in them. I'm just going to put our most beautiful images up here. We've got some great extended structure from our youngest disk, HL Tau. We have a new planet candidate over here. That's pretty fun. And PDS 70, which got the 2 planets like usual. Unsure if there's a third one there. But if you want to know more about this, if you're interested in one of the specific targets or all of them, or if you want to see our detection limits, then you can come talk to me. There's going to be 5 different publications that come out of this program. 3 of them are already published. You can see the names of the first authors above each target. And then there's 2 that are still in progress. So yeah, you can come talk to me if you're interested in learning more.
Hi, I'm Stefan Rankovic, and currently the community has found thousands of exoplanets, yet we've confirmed 0 exomoons. We're in the midst of searching 16 candidates, which we believe are more likely to have exomoons due to their large radii and long periods. I will walk you through how we've searched one of the candidates so far. In blue, we create the planet model and overlay that on the black light curve. In red, we take that planet model and reduce the radius to a quarter, keeping all of the parameters the same. That is our exomoon model. We then take that exomoon model and run it along this light curve with a single transit. We get that cross correlation result showing a large spike in the middle, which is high correlation between the exomoon model and the planet transit as expected. If we zoom in on the y-axis, we get these smaller spikes. Each of these could represent a possible exomoon transit. If we then zoom in on the spike just to the right of the transit, we get this, which looks like a dip, but we don't think it's an exomoon due to the shape and duration. But we're still very excited by this result as it shows the capabilities of finding exomoon-sized dips in a simple and fast method applicable to ESA Plato. Thank you.
Good afternoon, everyone. My name is Aniket Sanghi. I'm a first-year graduate student and NSF fellow here at Caltech. In just under a month, we are going to be executing a 44-hour JWST MIRI chronographic imaging program to try and answer the very exciting question, does our nearest sun-like star host planets or an exozodiacal disk? And I'm talking about Alpha Centauri A. As it turns out, pointing JWST at a 0th magnitude star that is moving by about 10 milliarc seconds per day is not a trivial task. You have to acquire a background Gaia star and then perform a blind offset to position Alpha Centauri A behind the coronagraph. This test image taken just this month on Sky shows that we can overcome these challenges and accurately place Alpha Centauri A behind the 4-quadrant phase mask. What kinds of planets can we detect around the system? What kinds of disks are we sensitive to? If you want to learn the answers to these questions, you can talk to me at poster number 41. Thank you.
Hi, my name is Vasudha Trehan, and I'm a PhD student at SUNY Albany. So as part of this project, which is a bigger project in collaboration with NASA, which is a grant funded by NASA, my focus is on machine learning aspect of this project, where I'm trying to build a machine learning system that will be used as a forward model to predict atmospheric absorption spectra that will in return will be used to predict habitability. So for this, I'm using data from already known planets in our solar system, which have already been recorded, and also the model data from GCM by NASA GESS. And by using both synthetic and the actual data, we are trying to predict the atmospheric spectra. And we are looking at the 30 dimensions aspect of this project. Right now in this diagram, it's just 2-dimensional phase. So we'll be looking at a 30-dimensional phase to predict habitability. To know more about my poster and the methodology I'm using, please stop by my poster. Thank you.
Right, everyone. My name is Maël. I'm a first-year PhD student in the CEA Saclay, and I'm going to have a poster on a very cool target. No, that. Okay, right. So it's a very faint target, very red, very low effective temperature, which is actually, this was the previous value of 350 Kelvin, but it's more like 300 Kelvin than right now. And it orbits a white dwarf. So I bet that you haven't seen many white dwarf planet spectra, and we have a really great one just over there. We have a lot of lines. It's really cool. The work I did on that, I took the raw data and did all of the reduction and then retrievals myself. So it's a complete self-consistent work. And we have amazing fits. You have the fits here in blue, so it is really well the ammonia line. I mean, everything is good. I mean, you have a good fit. Really exciting. You have the different PT profiles here with the molecules that are in the atmosphere. We have photometric data points that are also well fitted. And we have a lot of problem. I mean, the radius is too big, the mass is too low. It's really fun target. And the poster is huge. It's red and blue. And just after the stack stable. So it's, I mean, you can come talk to me if you are interested. Thank you.